everybody. Let's start. Before we start, I just want to say something. So after the class, I'm going to give you an information about the test that we're going to be having, how we're going to update on the test. So if I forget after the class, just remind me. So we've completed our 4 modules in this course. So the first module is on regression, which we completed last week. The second module is on transfer learning, which we are going to be starting today. Then the third module is on computer vision. Then the last module is on NLP, on natural language processing. So we are going to start the second module today. And the second module is on transfer learning, like I said. So before we actually start the module, under transfer learning, we are going to do computer vision and NLP tasks under transfer learning. So you should have a little bit of background on computer vision. So that's what we are going to use to start today's class. So there are, for computer vision tasks simply deals with using images or video streams to actually understand what is happening in the video or image. So that's what computer vision is all about. So as the name implies, vision, so images and video. So these are there are some tasks that can be done using computer vision. And like I said, vision has to do with images and video. So the computer having to recognize what is in an image or what is in a video stream. So the different tasks that can be performed are listed here. Classification. And remember that when we started machine learning, when we started the different types of machine learning, we said under machine learning it's divided into supervised and unsupervised. Then under supervised you have classification and regression. So it's the regression task we just finished. Then we also have classification. Classification task just simply means the computer looking at an image, then trying to say which image is what. So what is in the image? Is it a person? Is it a chair or any object that is in an image? Then for the computer to do a classification task or any of these tasks that is listed here, there should be it should be trained using an AI model or any kind of model you have. So the first task is classification. So this is an example of classification. So the computer is able to know that this is a cat, this is a cat. Then we have semantic segmentation. Semantic segmentation simply means grouping or segmenting regions in the image that are the same. That's what semantic segmentation means. So if you look at this picture over here, which is the picture of semantic segmentation, the computer was able to segment the image into the sky. So it's not that this group of pixels, they are related. So this is the sky, then these are trees. It was able to segment these as trees, was able to segment this as a cat, and was able to segment this as grass. So it's just grouping, looking at the image and grouping the things that the regions in the image the computer thinks they are the same. That's what semantic segmentation is. Then under computer vision task, we have object detection. Object detection is simply detecting the different objects that are in the image. So is this a dog? Is a dog? This is a dog, and this is a cat. So it's just detecting the different objects that are in the image. Then instance segmentation is kind of a little bit similar with object detection. So in instance segmentation, it's able to determine the different instances of a particular object. For instance, it was able to detect that for these animals, there are 3 of them. So it's just almost similar with object detection, but in instance segmentation, it's able to segment it using color coding, like the dog segmented as red, the other dog segmented as green, the other dog segmented as cat. Then another computer vision task is key point detection, person pinpoint detection. So person pinpoint detection is just, as the name implies, is for detecting persons or human beings. So looking at the picture here, is able to detect the different posture of the person, of different people. So one was able to detect the posture as standing up, then another one was squatting, another one was like kneeling down. So that's a person key point detection. So these are the different computer vision tasks that can be carried out. So it's not only classification, though for the purpose of this particular class, we'll be looking at classification. So classifying objects as either maybe there is a cat, or it's an image of a dog, or it's an image of a person. So that's what we are going to be doing. Then, so we are going to start. So in order for us to understand, like I said, we are on transfer learning. But in order for us to understand transfer learning, we need to explain a little bit about computer vision. Then after that, we go into CNN. So CNN stands for Convolutional Neural Network, as we are going to be seeing. So computer vision is a computational method for analyzing and understanding digital images, as I've said previously. So you are able to look at the image and understand it, to classify it, or to segment it, or to determine what the person is actually doing, in the image. So that's computer vision. So let's look at this image over here. So this is an example of an image that we can run computer vision tasks on. Then under computer vision 2, we have this data set. So this is like the data set of handwritten numbers. So starting from 0 up to 9. So you can develop a computer vision task to be able to recognize the hand digits, a number that is written by hand from 0 to 1. So this data set of images of handwritten digits is called the mixed data set. So computer vision can be used to understand this handwritten data set and actually classify it. So this, in order for us to understand images, you should know that for an image, for instance, when we have this image, any image you have is made up of pixel values. So if this is the blueprint of the image, so and in the case of handwritten digits, so not the previous slide I presented was blank, then this one, the number 2 is presented as an image in which it is a black and white image. So where there is nothing written on is black, then where you have the number written on is white. Also you have the number 8. So this is a gray style image. So a gray style image is also known as a black and white image. So a black and white image, the range of values is between 0 to 255. So that's the range of values for a black and white image. So any image that is black, the pixel value is 0. For instance, this image now is black. So the range, all the pixel values in this image are 0. Then if you have a pure white image, the pixel, this image is divided into pixel values, and the intensity of the pixel value is 255. So like I said before, any black and white image or gray style image, the range of values is between 0 to 255. So if it's 0, that means it's a black image. The maximum is 255. So if it's 255, that means that it's a white image. Then this image here is in between 0 and 255. It's at the midpoint. Let's say it's 128. So you can see that 0 is black, 255 is white. So the middle is between 0 and 255. So let's say that maybe the intensity of this image, let's call it in the middle, let's say it's 128. So this is how a black and white image is represented. So black is 0, then white is 255. Then that's for gray style image or grayscale image or black and white image. Then we look at color images. So for color image, any color image is divided into, a color image as red, green, and blue components. So effectively, it has 3 channels. Colored images have 3 channels: red, green, and blue. But for grayscale images, it's only 1 channel they have. So 0 to 255. So any pixel intensity in a colored image has range of values between 0 and 255 for the red, green, and blue components. So that's for a colored image. So it has 3 channels, and the 3 channels are red, green, and blue. So for this particular image, which is red, so it's a colored image for red, you can see that for the red components, it's at the maximum value 255, but the other components are 0. So the green and the blue components are 0. So that's why it's a red image. The red component is the maximum, while the other components are at 0. So let's look at another image. So this is a black, color black now. So for the color black, everything, the red, the green, and the blue components, they are all at 0. So this is a black image. So because all of it at 0. Then let's look at color green now. For the color green, this is a color green. The red component is at 0, but the green component is at the maximum 255. Then the blue component is 0. So that makes it a green image. So if Okay, so I don't know, it's not responding. Can somebody help me? Eh? Okay, is this one? Okay, they are mine. Okay, sorry. Okay, so this green image is represented as, so like I said, any image you as the RGB component. So you can represent this image as 0, 255, and 0. So this is the red component, this is the green component, and this is the blue component. So this is how the image can be represented. Then we look at, so this is a black image, every one of it has 0. Then we look at this blue image. So the red component is 0, the green component is 0, but the blue component is 255. So in essence, all images that are colored, they are just a mixture of red, green, and blue component. So let's look at this color here, which is a little bit light green. So this image here has some components of red. Let's say that component of red, let's call it 80. So let's call it 80. Then the component of green, it's very high. Let's say it's 250. Then the component of blue is 80. So if you actually want to represent this image, it's 80, 250, 80. So these are the components of red, green, and blue in the image. So we are just dealing with plain images. But in the case, remember I told you that this is like, I was telling you that this is like the blank image here. So this is the blank image. So it turns out that all of these values here, all of these, each of these in these square boxes, they are called pixels. So each of them are called pixels. And for a colored image, each pixel will have a component of red, green, and blue. So for instance, this pixel now can have 80, 250, and 80. Then maybe this component can have another value, maybe 10, 20, 230. So this is how a computer sees an image. When a computer is looking at an image, is looking at it in terms of the color intensity of each pixel values. That's what the computer understands. But in artificial intelligence, we want the computer to actually make a meaning of this pixel information, and that is why we have to start with how the computer actually sees an image, then before we apply AI algorithms to that particular image. So when a computer sees an image, it sees it as pixels. So the image is made up of pixels, and it's just looking at the color intensity of each pixel. So it's looking at the color intensity. So what do I mean by color intensity? The composition of red, green, and blue in each pixel box in the image. That's what the computer sees, and that's what it understands. But using AI algorithms is able to do much more than that, which I've highlighted, like semantic segmentation, classification, key point detection. So let's go to for instance, this handwritten image. Now, so I said that this handwritten image is an image of 2 and is an image of 8. So what does the computer see? So this is a grayscale image. So it sees this, all of these that are black. How does the computer see it? 0, 0. So all of the black, it sees it as 0. Then the white, what value? 255, 255. So these ones here, they are between 0 and 255. So these ones here, yeah, maybe they are 128, 120, and 120. So you can also do like that for the number 8. So that is the way the computer sees it. So we are, like I said, we are going to talk a little bit about convolution. So CNN. So what is CNN? CNN stands for what? Okay, so CNN stands for convolutional neural network. So it turns out that we have the CNN. So you have the CNN and you have the ANN. So what's the full meaning of ANN? Okay, artificial neural network. And you know we've done ANN previously. Have we done ANN or not? Okay, we have done ANN. So let's try to review ANN. Then from reviewing ANN, we'll now try to describe CNN in the context of ANN. So it turns out that for ANN, you have neurons. So this is the number of neurons in your input layer. So these are your input layers, then this is the output layer. So it turns out that ANN and CNN, they are the same thing. They are kind of the same thing. The only difference between the ANN and the CNN is that before you actually, in CNN, you are dealing with images. So you are dealing with images. And remember that the computer sees image as pixel value intensity. So the intensity of the color intensity of each pixel in the image, that's what the computer sees. So it turns out that for CNN, if before getting to CNN, if you want to use an ANN problem, if you want to use ANN to solve images, tasks that are images, can somebody tell me what to do? So let me try to say my question again. For images, so let me just write it. For images, the computer, it sees an image as images as pixel values. So it sees images as pixel values. Then it sees it as the color intensity of each pixel value of each pixel in the image. That's how the computer sees it. So when the computer is looking at an image, it's just looking at numbers. So the numbers are the color intensity of each pixel. That's what the computer is seeing. For instance, if you have this image now, what the computer is just saying is that it's just going to break this down into an array. So the array is the pixel value of the color intensity of each pixel in the image. That's what the computer is seeing. So if we that's what the computer is seeing. So if we want to you have images now. Remember in the case of ANN, when we started ANN, we were dealing with numbers. But now we have images and when the computer is looking at an image, it's just seeing numbers. and the numbers are the color intensity of each pixel. So if we wanted to use ANN, can somebody tell me what we are going to do? So now we are not dealing with regression problem where you have your X and you have your Y. Now we are dealing with images, and the images, like we know, the computer sees it as numbers. So what are we expected to do if we want to use ANN to represent an image? Yes? Exactly. So it's very right. So you will just, since the computer is already seeing it as numbers, so and it's in a matrix form, all you just need to do is that you convert this matrix, which is an image of numbers, you flatten it. So what do you mean by flatten? Remember, maybe this image now, let's say is 220 by 220. So it has, the number of values it has is 220 times 220. So that's, can somebody just do the math? 22 times 22 is what? Yes? 48,400. So what you just need to do is that you convert this image into a vector. You flatten it because the computer already sees it as numbers. So once you flatten it and convert it into a vector, then you put this vector as your input. Then you get your hidden layers and your output. So let me go over it again. So when we're dealing with linear regression problem, we're dealing with numbers x1, x2, x3. So those are your inputs and will have your output. Now we are dealing with images, and luckily for us, the computer sees the image as numbers, as a matrix of numbers. So we've tried to understand the numbers, so which is the red, green, and blue components of each pixel. So now if you want to represent an image and you want to use ANN to do it, all you just need to do is to get the matrix of the image, which the computer sees as numbers. Then you flatten the image to a vector. Then that vector will act as your input. Then you can begin to add the hidden layers, then your output. So that is a way you can use to do an ANN problem. But there is a big problem with that. Can somebody tell me, if you use this method, the method is, we are 50% there already, but we are not there. So who can tell me what is wrong with this method? So once you just see an image, just get the color intensity, flatten it, and just feed it directly to the ANN network. Who can tell me what is wrong? It's a little bit right, 50% correct, but there's something that is wrong or something that is missing. Do anybody know? Yes, exactly. So she's very right. We've not done any pre-processing on it. So that's the correct answer. And the pre-processing we are supposed to do is convolution. So the only difference between ANN and CNN is convolution. Convolution. So that is the operation we are supposed to do on it before eventually feeding it into a neural network. So we will now start with what is convolution. So that's the next question. What is convolution? Convolution simply means applying a filter that adds each pixel value of an image to its neighbors, weighted according to a kernel matrix. So convolution is a mathematical operation that we are going to be seeing. And convolution uses a kernel matrix, as we have seen, and that kernel matrix is a kind of a filter. So it applies a filter to the image to generate another image, as it were. And so that is convolution. So we are supposed to do convolution on it. So this, according to the definition of convolution, you need a matrix, and that matrix is called the kernel matrix. So the kernel matrix is KERNEL. So you need a kernel matrix. So let's say this is the kernel matrix that we have. So the kernel matrix is going to be provided for you, or you can just randomly, the AI algorithm will randomly generate it. So this is your image. This is the image, and this is the kernel matrix. And we want to do convolution. So I want to describe to you the process of convolution. That's what I want to describe to you. So this is the image, and this is the kernel. So I'm saying that this is the image. Can somebody tell me why this is an image? Why is this an image? Yes, it's a matrix of pixel values. So these values represent what? Grayscale, yes. So the grayscale component of the image. So now we want to do convolution now. So what happens in convolution? So this is the image, like I said, and this is the kernel. So the kernel is 3 by 3 matrix. It's not like it has to be 3 by 3, but for this example, the kernel is a 3 by 3 matrix. Then what you have to do is that you have the image, you have the kernel. You take this kernel, then you overlay it on the image. So normally the image in this example is 4 by 4. So when you take this kernel, then you put it on the image that fits the image. So after doing that, what you are going to do is that each of these values, you overlay it here. So this here is going to be times 0, times minus 1, times 0, times minus 1, times 5, times minus 1, times 0, times minus 1, times 0. So what did I do? This kernel, this is the kernel. It was overlaid on the 3 by 3 section of the image. So you multiply it, then you add it together. So once you do this multiplication, then you add it together. So let's do it. This is 0, this is minus 20, 0, minus 10, 100, minus 30, 0, minus 30, then 0. So when you add it together, 0 minus 20 plus 0 minus 10 plus 100 minus 30 plus 0 minus 30 plus 0. Did you get 10? Yes, so it's 10. So can somebody tell me the next step now? Exactly. So this, yes, exactly. So you overlaid it. So now you are going to slide the kernel to the, you will slide it to the right. So now, you know, we did this section, we got 10. So now you will slide it to the right. Then you will now overlay the kernel on it. So let's do the same thing. So times 0, times minus 1, times 0, times minus 1, times 5, times minus 1, times 0, times minus 1, times 0. So we'll multiply each of the elements, then we add it together. So once we do that, we get the next value. So you can just confirm that when you slide it, you got a 10. Just the confirmation. So what's the next step now? We slid it to the left. So now you will slide the kernel. You will now take it down. Anybody understand? You take it down. So when you take it down, you do the same operation on it. So you multiply each of it, then you add it together, then you get this value here. Then the last step you are going to do. So after doing this, you get the value of 40. Then the last step you are going to do is, before the kernel was here, then you slide the kernel again to the right. So when you slide the window to the right, you overlay the kernel matrix on it. You multiply each element of the kernel with each element in the window you are on. Then you add it together, then you get 50. So when you do this operation, just confirm that you get the value of 50. So have you confirmed? You do the operation. So I want you to do this operation in your notes. Then confirm that the result is 50. Yes, the arrangement matters. You need to start from the top, then you slide it to the left. Then after that, you slide it down. Then you slide it to the right. So you slide to the right. After sliding to the right, you go down again. And you need to slide. So the arrangement matters. Okay, so that's the convolution operation. So you have, this is your image, this is your kernel, and this is the result of the operation. So that is the convolution operation we have. So this is another convolution operation where this is the image, this is the kernel. So, and this is how to do it. So you just overlay the kernel on the image, then you sum it together. So that will give you the result. Yes. I'll come back to that later. So she asked a good question. That so her question is a very good question. So the question she's effectively asking is, for instance, this is a 4x4 image, and this is a 3x3 kernel. So what is the output supposed to be like? So as you can see, you have a 4x4 image, you have a 3x3 kernel, and the result is a 2x2. So there is how you can find out what the dimension of the output should be. So I will come back to that later. But what we are focused on at the moment is for you to be able to know how to do the convolution. So this is a convolution operation that's been done on that. So it turns out that, for instance, if you have this image now, so this is the image, and like I said, what the computer sees is not actually, because when we look at an image, we are not actually, we as human beings, we are not looking at it as maybe pixel values, the numbers in the image. What we are looking at is that we are looking at objects and everything. So it turns out that the reason why we do convolution is a filter. When I was defining, in our definition of image convolution, what did we say image convolution is? We said applying a filter that adds each pixel value of an image to its neighbors, whether according to a kernel matrix. So the keyword I'm actually looking for is a filter. So for instance, if you have this image, this is the original image. So it turns out that if you apply convolution, this is the result of the convolution, because you have an image, you are applying convolution, then you are getting an output. So it turns out that if that previous picture is the original image, then the filter, you have the filter, then it turns out that this is the output. So the output is also an image. So can somebody tell me, looking at the original image, then the convolved image, the result of the convolution. So let me show you the original image again. So this is the original image. Then this is the result after you do a convolution. Can somebody look at this and tell me what is convolution actually doing? Okay. Another explanation in more technical terms. What do you feel convolution is doing? Okay, that's one. Another, do you have a different answer? Okay. Yeah, it converted it to grayscale. But apart from that, in addition to that, what else is convolution doing?
Segmentation.
What is convolution mean? Okay. Inverse. Compression. In addition to that, you want that. Anybody? All of you are right. So conversion based skill, yes. Segmentation is almost there. Is yes, it generated another image. So segmentation is almost there. So what else is it doing? Okay. Yes. So it's actually the one that is actually getting close to the answer. So let me just tell you what it's doing. It turns out that convolution, in addition to all what you have said, what convolution does is to extract the corners, edges, and circles in the image. So convolution extracts the edges, the corners, the circles in the image. That's what convolution is doing. Extracting the corners, circles, and edges in the image. So you have the original image here, but then in the original image, the edges, the corners, the circles, or the dimensions, they are not well pronounced. So what convolution will do is to extract all of this. So it's extracting some features. In other words, it's extracting important features. So apart from extracting the edges, corners, and circles, it's extracting important features in the image. So when it said segmentation is also extracting corners, circles, and some of the dimensions. So that's why it was correct, but it didn't actually use the right word that I wanted him to use. So that's what convolution does. So one person made a very good point. He said it's compressing the image. So he's right. Another use of convolution is to compress the image. So why is that? Remember when we did that operation, it was a 4x4 image, but then what was our output? 2x2. So it also compresses it. So that is also a function of convolution. So apart from extracting features in the image, it also compresses it. So that answer is very correct. Yes? Yes. Header matrix is the filter. So another filter, the AI algorithm is going to randomly generate a filter for you, or it's going to be given to you. It did convert it to black and white. Can you see that this is not black and white? So it did actually remove the colors. Some of the color components is reserved. No, it's not wasted. It's not wasted. The some color components involved. So thank you for that observation. So his question was, isn't the color component an important feature in the image? So the answer is that convolution preserves the color components. It doesn't convert to grayscale, because when we see this result, we can still see some color components in terms of the trees, I think. So the color component is preserved during convolution. So apart from convolution, like when I was trying to explain to you CNN, so I said the difference between CNN and ANN is that convolution. So apart from convolution, there's an operation that is performed alongside convolution, and that operation is called pooling. What is pooling? Pooling is reducing the size of an input by sampling from regions in the input. So let's do an operation. We have different kinds of pooling. We have max pooling and we have average pooling. So let's do an example of max pooling. So if you have, for example, if this is the image now, if this is the image, so you have, this is your image, then what we are doing, we are not doing convolution now, we are doing max pooling. So what max pooling does is that you're going to specify the dimension of the max pooling. So for instance, if our max pooling, the dimension we specified is 2 by 2. So what with this max pooling, what is it going to do? This is the original image. It's going to take a 2 by 2. It will get the maximum. So what's the maximum of this? 50. So it's going to put 50 here. Then it's going to take the next 2 by 2. It will get the maximum. The maximum is 110. It will take the next 2 by 2. It will get the maximum 20. It will take the next 2 by 2. It will get the maximum 40. So that is max pooling operation. So you need to know the difference between max pooling and convolution. Okay. I'm coming. Let me just show the result. So this is the result of the max pooling. Yes. There's no filter. Thank you. Because you know, for that convolution, a kernel matrix was specified as the filter. But here, there is no filter. It's just the dimension you want to get the average of. Like now, the dimension you want to get an average of is 2 by 2. So every 2 by 2 will take it and we get so you know the average, the maximum. So that's max pooling. So you just the maximum of this, the maximum of this, the maximum of this, and the maximum of this. So that's max pooling. I'll still come back to this later. But in max pooling, you will just get the first 2 by 2. Then you wouldn't slide. You will get the next one that you've not gotten before. So for the first one, we got this. For the second one, you get the next one. Then you get the next one, then you get the next one. So you are not like sliding like we are doing in convolution. What is it? Yes. Yes. So, is there any other question? Yes. No, it depends on the algorithm. So if it's 2 by 2, then use 2 by 2. If it's 3 by 3, use 3 by 3. But in this example, we are using a 2 by 2. In this example, we are using a 2 by 2. So you take a 2 by 2, you take the next 2 by 2, you take the next 2 by 2, and you take the next 2 by 2. So that is max pooling. So like I said, we have 2 types of pooling. We have, the first type is max pooling. So the max pooling is to get the maximum value. That's max pooling. Then the second type of pooling is average pooling. So in your notes, using this example of the image, can you tell me average pooling? Though I've not said how to do it. So just do it in your notes. Average pooling. Tell me how you do the average pooling. So in max pooling, you get the maximum. So 2 by 2, you get the maximum. So can you do average pooling now in your notes? Or somebody should tell me. So how will you do average pooling? Exactly. So you just find the average. So you do this, get the average, then you put it here. You do this, get the average, you put it here. You do this, get the average, put it here. Then the last one, you get the average, then you put it here. So that's average pooling. So that is average pooling. So before we leave pooling, can somebody tell me, like I asked the question that what is the function of convolution? Then we found out that the function of convolution is to extract important features in the image. So I'm asking the same question. What is the function of pooling? What's the function of pooling? Exactly. Who said that? To reduce the size of the image. Yes. So that's the function of pooling. So the function of pooling is to reduce the dimension of the image. That's the function of pooling. Though in convolution, we said that convolution too can reduce the size, but max pooling is the actual one that convolution reduces the size, quite alright. But the main function of convolution is to extract the features in the image. Then the main function of pooling is to reduce the size. That's the main function of pooling. Do you have a question? Okay. So we are now in CNN. So what do we do in CNN in comparison with ANN? So remember before we started, I said that a computer, it sees an image as just numbers of pixel values. So I said that if you want to represent an image, you want to do artificial intelligence tasks on an image, you can just get the image, you flatten it, then just apply the ANN. But what we've now discovered is that when you take this image, before you feed it straight up to ANN, you have to do some certain things. And the things we did, you have to apply convolution first, then you have to apply pooling, then eventually you can now feed it into an ANN. So that's the major difference between ANN and CNN. So for ANN, you are dealing with regression problems. So these problems are numbers, like Excel formats, data in Excel format. But in CNN, you are dealing with images. So you can take true routes. Since the computer sees the image as numbers, you can just convert, it's already numbers, that's what the computer is seeing. So you can just flatten it and just feed it into the ANN. But we said that that is not the ideal case. You need to do some pre-processing. You need to convolve, then you can do some pooling. Then after that, you can now flatten it, then feed it into an ANN. So that's just the difference between convolution, CNN and ANN. So it turns out that in CNN, it's not just one convolution and pooling that you can do before you feed it into the ANN network. You can do multiple convolution and multiple pooling. So this is the first. Pooling is always followed by convolution. So when you get the original image, you can do the first set of convolution and pooling to extract the low-level features and to compress it. You can do the second set of convolution and pooling to extract the high-level features. You can do the third, fourth, fifth set of convolution and pooling. So it's not only just one set of convolution you can do. You can add pooling. You can do as much as you want in order to get the best model. So this is one of the papers I put on review, deep residual learning for image recognition. And this paper had the highest citation, like in the whole of AI. This is the paper with the highest cited paper in the field of artificial intelligence. It had more than 400,000 citations. So this particular paper, how many persons reviewed this paper in the first assignment? Okay. So let me show you this paper, the network. So it turns out that they describe 3 architectures, and the 3 architectures are all convolutional neural network. So in this VGG19, you have the image. Remember I said you will start with the image. Then what did they do? They applied a 3x3 kernel filter on the image. They applied the first set of convolution, they applied the second set of convolution, then they did pooling to reduce the dimension by 2. Then after that, they applied 2 sets of convolution, then they applied pooling to reduce the dimension by 2. They applied 4 sets of convolution again, they applied pooling to reduce the dimension. Remember I said pooling is to reduce the dimension by 2. Then they applied another set of convolution. Again, this set of convolution, then they applied pooling to reduce it by 2. Then after that, it was flattened. So they applied these layers to flatten the image. Then of course, to produce the output. So So that is the structure of VGG19. I'm sure you must have been hearing of VGG19. So why is it called VGG19? When you count the layers of convolution, when you count the layers of convolution is 19. Let me zoom, then you try to count it. Okay, so let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That is why it's called VGG19. For this layer is ResNet. It has 34 layers of convolution. So you can just count it. So it's 34. Then if you also count this one too, it's 34. So all CNN structure, they follow this. So you have to do convolution, then pooling, different sets of convolution. Like I said, this 3 by 3, this 3 by 3, this 3 by 3 is the kernel size. But I'll still come back to this. So what do these values mean? Does somebody know before I explain it? So this one, 3 by 3, is the kernel size. Yes, for the convolution. So these values, I'm not mentioning it, but who knows what they mean? Number of bits. Number of bits. Okay. Any other one? Pixel value. Okay. Any other contribution? If the person sleeping on that, but just wait for tell him to stand up. Stand up. Okay. It's not compulsory to do a pooling after composition. So it's not compulsory. No. Okay. For ANN, only one way of that. That's ANN. Yes. So these numbers, who know what they mean? Oh, who can guess? Yes. Now, it's not bits, it's not pixel. It's not number of neuron. It's not number of neuron. Who can guess what these numbers, what they mean? No, it's not the scale. So let me just tell you what those numbers mean. Those numbers, it means the number of channels. Yes, channels, that's what it means. It means the number of channels. So, where does the number of channels, where does it come in? So remember for an image here, this is the image. So let's say it's a 220 by 220 image. And let's say it's a colored image. So remember I said in a colored image, it has the red, green, and blue components. So it turns out that this image, please keep quiet, please. Please keep quiet. So it turns out that this image is a 220 by 220 by 3. 3 is the number of channels. Where does 3 come in? Yes, so the red, green, and blue components. So actually the matrix that for a colored image, it has red, green, and blue components. So it turns out that this image, this is what the computer is seeing. It's seeing 3 matrices. One is for red, one is for green, and one is for blue. So those numbers I was saying, they are actually the number of channels. So when you are doing convolution, like for instance now, you take this image, you do a convolution operation on it. After you do the convolution operation, you get a 220 by 220 by. So it is possible to specify the output, the number of channels you want for your output after the convolution. Remember that the original channel you started with is 3. So you can decide to say it's 64 you want. So what this means is that the result of the convolution, instead of it being a 220 by 220 by 3, you want it to have 64 channels. So now it just has 3 channels. So in other words, you are going to get 64 matrix. So this is the matrix, but you get 64 matrix as a result of the convolution. So your next question can be, how can you get 64 matrix? So what the way you can get 64 or any number, you can specify this. You can specify, it doesn't have to be 64, but it has to be a factor of 2 raised to the power x. But it doesn't have to be 64, it can be 128, it can be 510. So what this is saying is that when you are doing the convolution of this, do it 64 times. So in other words, the kernel matrix, that kernel that is acting as the matrix that you are doing the convolution, you know that it is just 3 by 3. So what you are saying is that specify 64 of this kernel matrix, and there will be difference. What is in the first? If this is the first kernel, this is the second kernel, then this is the 64th kernel. So what is going to be in this? Each of these kernel matrices are different. They are going to be different. So what he's saying is that specify the number of kernel matrix, and each of them will be different. So that when you are actually doing the convolution, you are doing it 64 times using different kernels, using 64 different kernels. So that's why this number comes in. It is the number of channels, the number of kernel matrix that you want to apply on your image to do the convolution. That's where it comes in. So you start with a 3 with the size of the image, then 3 is the default number. Then when you are doing convolution, you specify the number of channels, so the number of kernel matrix, which I said are different. So the first one is different from the second one, it's different from the third one, and it's different from the last one. So you are effectively doing 64 convolution. So that number represents the number of channels. So let me go back to that paper. So this is the paper. So what this is saying here is that you are doing convolution in 3 by 3 kernel, but 64 times. So 64 different convolution. So what this one is saying is that the second set of convolution, 64 kernels, so 64 times. So the output is, I want you guys people to pay attention. So here, when the size of the image is 224 by 224 by 3, so 3 representing is a RGB image. So after this point, the size of the image is 224 by 224 by what? 64. At this point, the size is 224 by 224 by 64. At this point, you did a pooling, and the pooling divided the size of the image by 2. So at this point, the size of the image is 112 by 112 by what? By 128. Because you are now doing 128 different convolution. at this point 112 by 112 by 128. When you get to this point, you apply the pooling, and the pooling divided the image size by 2. So 112 divided by 2 is 56. So the size of the image is what? 56 by 56 by 256. So the same thing, you get to this place. But when it comes to this place, it has divided this by 2. So it becomes what? 28 by 28 by 512. So let's scroll down. Let's continue to get the dimension. So let me leave it at this point. So when we get to this point, it was formerly 14. So at this point, is 40 by 40 by 512. So yeah, we applied pooling to divide by 2. So after we divide by 2, it becomes 7 by 7 by, so it becomes a 7 by 7 by 152. Then here, from this point to this point, we actually we did a pooling to divide by 2. Then after that, an average pooling was applied here. And that average pooling was just to get the average of all the numbers. So from this point, let me try to. So from this point, when you get the 7, the average was gotten. I will still go into details later so that you fully understand. So it was that average that actually flattened it. So the average actually flattened it. So you add a 7 by 7. So let's say that this is the matrix. 7 by 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is the matrix, 7 by 7. Then how many times? So the last set, what it did is that it got the average of this, and it used a 7 by 7 pooling filter so it just got the average of this. So once it got the average, it got a single value. So that's why the size is 1. Then you have the fully connected layer, which is 4096. So that's the structure of the VGG net. Then this is the structure of this is called the ResNet 34, and this is the plain version, and this is the residual version. So this is the structure of CNN. So you do convolution, then pooling. So like we said, like we read in that paper, it's not like compulsory that after convolution, after every single convolution, you do pooling. So like they did sometimes 3 sets of convolution, then later they pooled. Then maybe another set of convolution, then they pooled. Then after that, it was flattened, and you eventually feed it into an ANN network. So that's the structure of CNN. So let's go back to this slide. So we can see different structure of CNN. So in order to do CNN operation, we've already done it But this is the mathematical expression or mathematical equation to represent convolution. So you multiply, remember we're multiplying each element of the kernel with each element of the image. So remember we were doing that. So this is where it comes in. After multiplying, you sum it together. So this is where the summation comes in. So this is the equation for convolution. Then we've talked about convolution. So CNN, please keep quiet, please. So CNN is a deep learning algorithm that takes an input image, assigns important weights and biases to different aspects of the image, and is able to do classification or the computer vision problem. So it's able to successfully capture spatial and temporal dependencies in an image. So through the application of filters. So those convolutions, they capture features in the image, spatial features and temporal features. So the architecture performs a better. So I'll just allow you to read it because I've explained most of this in the explanation. So this is a CNN network. So can somebody describe this CNN network for me? Can somebody describe it for me? Okay, so this is the input image. So why is it 28 by 1? Yes. So what this means is that this is 28 by 28. Then it's grayscale. Then after that, convolution was performed. And the convolution converted this to 24 by 24 by N1. This N1 represents the number of channels. So how many convolution was done? You can count it 1, 2, 3. So if you look at this image, it was just grayscale. It just had one channel, but they did convolution on it. How many times? Let's just say 16 times. So you can see that there are 16 of it. Please, do you all understand? There are 16 of it because they did convolution. The kernel matrix is a 5 by 5. So they did convolution on it, but they did it 16 times with 16 different kernels. That's why the output is 16. So this is 24 by 24 by 16. So now, what was done here? So 2 by 2 means the image is divided by 2. So 24 divided by 2 is 12 by 12 by the number of channels. They now did another convolution using the number of channels. And after that, they did max pooling to divide by 2. Then after that, they flattened the image. So these are different matrices. So the image was flattened so that it's now a vector. And after flattening it, you can now connect to an artificial neural network. So that's the explanation for this network. So this one is just also, we've already done this, how to do convolution. Then there's something you should know about convolution. Please keep quiet. You in black, please keep quiet. There is a concept called padding in convolution, and we've not talked about it. So I want to describe the concept of padding in convolution. So what padding does is that Okay, so what padding does in convolution? Padding is a very, very important concept in convolution. So please pay attention on padding. I've not mentioned what padding is. So it turns out that okay, so let me describe the concept of padding. Please pay attention. Or before I describe it, who knows how to pad before we do convolution? Okay, so let me just explain it. Please pay careful attention, please. Okay, in that example I gave you, the first example of convolution, the size of the image was a 4x4, right? The size of the kernel was what? Okay, it was 2x2. 3x3. That was the kernel. Then this is the image. Then the result. What was the result? It was a 2x2. So it was a 2x2. Okay. So thank you very much. So this is convolution. Okay. Please pay careful attention, please. So this is convolution, right? Okay. So when I asked you people, what is the function of convolution? Someone mentioned is to reduce the size of the image because we started with a 4x4 and we ended with a 2x2. So maybe that was the reason why somebody said that it is to reduce the size of the image. But when we moved ahead, we discovered that it is not actually convolution that is reducing the size. We have another thing again that is will reduce the size for us, and that one was pooling. So it turned out that convolution is not originally used to reduce the size, though in the process it reduces the size, but that's not the work of convolution. The work of pooling is to reduce the size. The work of convolution is not to reduce the size, but we now discovered that eventually the size is reduced, which we don't want. So we don't want to reduce the size of the output. We don't want that size to be reduced. We don't want it in convolution. We just want it to extract, just to do its work and leave the size of the image, the original image. We want it to leave it the same as how we meant it. We don't want the output size to be reduced because that's not the work of convolution. And that's where padding comes in. So what do you do in padding? For instance, this is a 4x4 image. So it's a 4x4 image, right? If we introduce a padding of 1, please listen carefully. We introduce a padding of 1. Can somebody tell me that original image, the values that were inside? 10, 20. Okay. Okay. Okay, 40 and 50. So thank you very much. So this is the size of the image. Then like I said, the concept of padding is we don't want, after convolution, we don't want the size of the output to be different from the input. We just want it to extract the features, that's all. I want to maintain the size. So what we can do is, let's introduce a padding of 1. So this is the original 4x4. It started from 10, then it ended at 50. So we are going to apply a padding. Please listen carefully now. A padding of 1. So now I'm applying the padding now. So now this is my padding. Then I can just put a 0 around the original input image. So remember, the original input image was 4 by 4. Then when I apply a padding of 1, what's now the dimension? A padding of 1, what's the dimension now? 6 by 6. 6 by 6. So now you apply a padding to the original image. So it is after applying a padding, you will now do the convolution. So if we do a convolution of an image that is a 6 by 6, can somebody determine the size of the output? What will it be? No, you have to tell me with reason. If we do, now we've applied a padding of 1. So we now did the convolution now. What is going to be the output? The size of the output. You are just guessing. What will be the size of the output? Why? Why? Can you do it? Tell me. I want you to do it in your notes. This original image, apply a padding of 1 and put zeros around that padding. Then apply that kernel, that same kernel. Then do the output. Do it in your notes. Let me go around. I want an answer. Once somebody is done, let the person tell me. Then let's do the confirmation. What is going to be the output? The size of the output. So the first person to do it, to just simplify, so that we confirm that same image. The only thing you are now doing is to apply a padding. Then let's get the output. So please start using your notes. Every one of you. The reason why you are padding, like I said, is to get it safe. You don't want the dimension of the you don't want to reduce the size. That's what you're padding. Please, it's convolution. It's not pulling. And it's not pulling out. Convolution. Convolution is different from okay. So somebody yes, somebody has gotten the first stroke of convolution. This is convolution you are doing. Not pulling. Not pulling. It's not convolution you are doing. Okay, it's not pulling you are doing. Yes, it's convolution. It's convolution you are doing, not pulling. Pulling is different from convolution. Some people are doing pulling. It's not pulling you are doing. It's convolution. A lot of persons have got a lot of people are doing pulling. It's convolution you are doing. Convolution is different from pulling. Please, not that I made a mistake. Please try to do the right thing. Don't just do that bad. It's from the evolution of question is different Please be quiet, please. So there are some persons that some people are doing the wrong thing. So, and they are getting the wrong answer. Some persons have done the right thing and they've gotten the right answer. So when you apply a padding of 1, then you do the convolution on a 3 by 3. The size of the output is a 4 by 4. Those people that did the right thing is a 4 by 4. That's the output. So from those people that got the answer correctly, what padding does is that it preserves the shape of the input. So like I said, originally if you are doing convolution, it is going to reduce the size of the output image. But we said that that's not the work of convolution. If you want to reduce the size of the image, it is pooling that you use. So what we did in order to maintain the size or the dimension of the input image, you apply a padding. It can be a padding of 1, it can be a padding of 2. So originally this is the dimension of the image. It's a 4 by 4, but we applied a padding, so it now became 6 by 6. So when you apply convolution, you will get 4 by 4, which is the original size of the original image. So what padding does is just to put zeros around the image so that the original dimension is maintained after the convolution, because you don't want the dimension of the image to reduce. So that's the function of padding. Can somebody tell me, yeah, we applied a padding of 1. How do you apply a padding of 2? What are you doing if the question says apply a padding of 2? Yes. So you add another set of 0 to the outside box. So you add another set of zeros to it. So 0, 0, 0. So it will become. So what will be the dimension now? Yeah, so it will become 8 by 8. So that's the concept of padding, because you don't want the dimension of the output to reduce. Let's go back to this paper, which is the most highly cited paper in the field of artificial intelligence. So, can you see that? Please keep quiet, please. Those of you disturbing, please keep quiet. So, can you see that this is the size of the input image? 224 by 224. That's the size of the input image. 224 by 224. So after applying convolution is supposed to reduce the dimension. But after applying this set of convolution, the dimension was still the same. So that means that you can imagine that a padding was applied. That's why this dimension. So let me tell you the formula. For instance, if the size of the image is a 4 by 4, that's the size of the input image, and the size of the kernel is a 3 by 3. The formula to know the size of the output is the input minus the size of the kernel plus 1. So you know that the dimension of the output is a 2 by 2. Like that question I gave you that I said you should apply a padding. So it was 6 by 6. That was the input image. The kernel was still 3 by 3. So to know the dimension of the output is 6 minus 3 plus 1. So you know that the dimension of the output is a 4 by 4. So that's how to know the dimension of the output. So when you do this calculation and you are not getting this dimension, you know that obviously you are doing the wrong thing, which is what some of you are doing. So here, this is the size of the input image. Now, they applied a 3 by 3 convolution. Normally, if they didn't apply padding, what is supposed to be the size of the output if they did not apply any padding? The kernel size is a 3 by 3. The size of the image is 224 by 224. If no padding was applied, what was supposed to be the size, the dimension of the output? Okay, it was supposed to be 222 by 222, but we can see that that dimension did not change. So that means that they applied a padding there, the padding of 1, even though it was not stated there. So, like I said, the function of convolution is not to reduce the dimension. It's just to extract the features. So in order to maintain the dimension, you can introduce padding. Then one last thing before we end the class is the concept of stride. Apart from padding, there is a last thing you should know of, which is called stride. So that's the final concept you need to understand. The concept of stride. So what is stride? Stride is, so let me explain it using that example. That example we're working with. Please listen carefully to stride. So please listen carefully to what is stride. So this was the size of the input image. So it was a 4 by 4. It started with 10 and it started with 50. That's the input image. Then this is the kernel. The kernel is a 3 by 3. Just tell me the value of the kernel. Let me just start with 0 and end with 0. So this is the kernel. So like I said, the last thing after this stride, that's all. So it's the concept of stride. So what happens in stride? So let me just write that. So I want to explain to you the concept of stride. Please listen carefully. So when you are doing convolution, so we are still on convolution. We're still on convolution. So now when you are doing, if the concept of stride is introduced, so first of all, you take the kernel, then you overlay it, then you get the first value in the output. So maybe this is your first value after doing the convolution. Then what you found out that what what we have been doing previously was a stride of 1. The stride indicates how you slide, by how much you slide that Kenyon matrix. So after this, we slid it by 1, then we got the next value. But if you say the stride is changed to 2, if the stride was changed to 2, that means that you should shift it by 2 pixels. So you are not shifting it when you are doing the next one. You are not shifting it by 1, you are shifting it by 2. And you will do the convolution. So obviously, probably you've applied padding to it. So this is the padded value. So you shift it. Now the stride is equal to 2. You shift it, then you do the convolution. Then you move down again. So you move down again. Remember that when you are moving down, the stride doesn't count. It's when you are moving to the right. That's when the stride counts. So after doing this first one, instead of moving 1 space, instead of going by sliding by 1, you will slide by 2. Because the slide is now 2. So you will slide this way by 2 pixels. That's where the concept of stride is introduced. So previously, we're just assuming a stride of 1. So if the stride is specified, so you know how much you move, how much you slide to get the next result of convolution. Please, does anyone understand what I said? Please, do anyone understand? Before question. Okay, so what's the question?
I said you slide.
Yes.
How many units? Now like
okay. So for instance now, maybe this is a stride of 2. Let's try to do it. So we get this value which is here, then we stride again, maybe we get another value, then you slide again, you get this value, you stride again, you get another value. So a thing is a square. What is it? Okay, yeah, there will be a padding. Okay, so maybe there is a padding here. Okay, so I will talk about that tomorrow. So the time is up. So we'll continue the class tomorrow. Yes. So, okay, so for your test, please keep quiet. The way I'm going to assess your test is going to be in form of continuous assessment. So what that means is that I will not just use a single test and just say that is your test 1. So it will be composed of different things. So what your test 1 is composed of is the assignments and the class exercise. And those class exercises, assignments have been given you. So that one is going to be 5%. So remember that your test 1 is 15%. Then I'm going to give you a project based on the modules you've done. So we've just finished the regression module, and now we're in the transfer learning module. So I'll give you 2 projects. So that one will constitute 5%. So the 2 modules. Then I will give you an assignment, a test 1 assignment. That one is going to be 2.5%. Then I will now give you a quiz, a test 1 quiz on module next week. So next week is test 1, but it's going to be a quiz. It's a multi-choice question, and that quiz is just going to be 2.5%. So when you add everything together, you will get your 15% for test 1. So tomorrow, next week, Tuesday, from 5 to 6, you'll be able to do the test 1 quiz. But that's no, yes, Tuesday. I will put up the quiz on module. So it's only between this time you'll be able to do the quiz. So I'm not going to be with you. You can just do it anywhere there is internet connection. So like I said, that one is just 2.5%. So all the assignments I've been giving you, most of you are not doing it because according to my list, you people are 80. When I see what's on module, it's only like 60 something persons that have submitted. So just know that your marks are going, and those of you that will do it, you will not do it correctly. Like I will say you should do this and this and this, but I'll tell you to do 5 things. It's only 2 things you will do. You just know that your marks is reducing. Then the projects, like I said, there are 2 projects. One for the regression and one for transfer learning, which you can still 5%. Then I'll give you a test 1 assignment, which is 2.5%. Then the quiz is just 2.5%. So that's the module, that's the lecture I'm going to use for your test 1. So by the time I add all of this together, it will give me your 15 marks. So that's what I want you to know. Then I will give you the first project now today because we've completed the first module. And I'll give you the second project after we complete the second module. So what's the first project on? Okay, what's the first project on? So I will put up, okay, sorry. Okay, so I will put up this, please keep quiet, please. So this first project is called regression project. So what is this project for? Please listen carefully. This project is based on the regression. When we're doing regression, it was 2 assignments against 2 data sets. One data set was the auto-MPG data set, and the other data set was the juice card data set. Those were the 2 data sets we worked on for the regression problem. So this project, please listen carefully, is to get another data set. Please listen carefully, is to get another different data set and perform all of the same operations we did when we were doing the class, when I was teaching you, the same operation. Is to get another data set. No 2 persons should work on the same data set. So how will I monitor it? I will share this spreadsheet with you. Once you've decided the data set to use, you will just fill a row. You will type the data set name, where you got the data set from. And once you've done that, no other person should choose that same data set. Please, the instruction is no 2 persons should use the same data set. That's the instruction. And that's why I've provided this spreadsheet. Once you've determined and you've gotten the data set, you just quickly type your name and just put in your data set so that another person will not come and use that data set, because that's the instruction. So what I mean by you should perform the same operation that we did is that it's a regression data set. So it's not image, it's Excel format. That's the data set you are going to be using. So you will just, all of the procedures we followed, where we had the continuous attributes, we had the categorical attributes, then we knew how we pre-process the continuous attributes, we knew how we pre-process the categorical attributes. Then after that, we combine it together, you add your hidden layers. Of course, you will divide into training, test, validation, you shuffle, you apply activation, Then maybe you can normalize if you want, then your output. So what you are doing should follow all of the procedures that we followed when we were doing it in class. So that's the regression project. Please, is there any confusion with what I've just said? Okay, so that's the regression project. So like I said, I will make this link available on Moodle so anybody can edit it. Once you've chosen the data set, if I see two people using the data set is 0, and you can see that for the project it carries 5%. So no two persons should work on the same data set. That's the instruction. Okay, thank you very much.